When the sky is murky, tabletop the labs, analog gravity and synthetic spacetimes. When the sky is murky, you bring gravity to heel on a bench. That sounds absurd until you watch a cloud of atoms drop to billionths of a degree and start behaving like a single quantum thing. In a Bose-Einstein condensate, sound becomes a first-class citizen. And with the right flow, sound waves see an effective geometry, an acoustic spacetime. You can sculpt with lasers and magnetic fields. Here's the move. You build a narrow channel in the condensate and drive a flow that's subsonic on one side and supersonic on the other. There's a boundary where the flow speed equals the sound speed. On that boundary, phonons can't claw upstream. That's a horizon. It's not metaphor. The math lines up. The wave equation in this flow looks like a scalar field in curved spacetime. The question that kept people up at night: if horizons are real in a fluid, do they radiate? The stakes were heavy. Hawking radiation is a thermal whisper predicted for black holes. Pairs of quanta birth near the horizon. One escapes, one falls in, and the whole slowly evaporates. If a lab horizon threw a thermal spectrum, you'd have a concrete example of gravity-like behavior emerging from fluid dynamics. It wouldn't prove spacetime is a condensate, but it would punch a hole in the idea that geometry must be fundamental to get horizons and heat. Action, not theory. Teams spent years taming noise. Condensates are fragile. Horizons slip if the flow jitters. Detectors must read out density ripples at the level of a few atoms. Early claims drew fire. Were those correlations thermal or artifacts? Then came a major turn. Multiple groups reported analog Hawking radiation with thermal spectra, tunable horizons, and cross-correlations between Hawking partners consistent with a horizon as the source. Change the flow profile, the temperature shifted as the effective surface gravity changed. Slide the horizon, the signal followed. One grad student, eyes rimmed red from a week of night shifts, listened to what looked like thermal noise, mapped it to the horizon position, and realized it wasn't noise anymore. It was the horizon talking. Meanwhile, black hole lasers moved from thought experiment to table. Set up a pair of horizons in a flowing condensate, an inner and an outer, and certain modes bounce back and forth, amplifying via superradiance. Energy flows from the background into the oscillation. The lab saw it. Drive the right profile and the trapped region rang on its own, a feedback loop of horizon physics in miniature. It was eerie and oddly domestic, a cosmic engine whistling inside a vacuum chamber the size of a shoebox. Parallel action, effective light cones. In these media, excitations don't travel at the lab speed of light. They move at a sound speed set by density and interaction strength. By shaping the density, you bend the effective metric. Researchers painted flows that mimicked expanding universes, sonic analogues of de Sitter spacetime where phonons redshifted as if the universe inside the condensate were stretching. Turn a knob, watch wavelengths grow. You could almost hear cosmology as a hum. Now the caveat that keeps everyone honest. Analogy isn't identity. BEC phonons aren't photons. Their gravity comes from hydrodynamics, not Einstein's equations. Back reaction, the way radiation saps energy from the horizon differs. Quantum entanglement across the horizon looks similar in correlators, but the field content is not the standard model, so we don't get to declare victory. What we do get is a proof of principle. Horizons are kinematic, not sacred. Thermal emission can arise from the structure of the wave equation in a flowing medium. That's enough to tilt intuition. If nature already uses fluids to fake geometry in the lab, maybe geometry in the wild can emerge from a deeper substrate and still pass every test we've thrown at it. Here's where it gets practical. Flow profiles become engineering. The same equations that tell you how to shape a horizon tell you how to route excitations, how to confine, how to leak. Metamaterial folks took notes. Build boundaries that guide modes, and you tailor the vacuum's allowed fluctuations, Casimir on demand. In a way, the lab's horizons and cavities are both about boundary-caused spectra. One is static plates squeezing modes. The other is dynamic flow carving a one-way gate. Together, they teach you to think in terms of spectra and geometry you control. Human stakes are vivid here. A postdoc leans over a chilled glass cell, fingers hovering, breath held to keep from fogging a viewport. The scope shows ripples, tiny density waves fanning from a region they spent months stabilizing. The pi whispers, shift the detuning. The flow profile eases. The thermal peak slides. Someone laughs quietly because it's working, and that rarely happens on schedule. Down the hall, a skeptic watches the analysis code and keeps asking for blind swaps, synthetic injections, anything to prove the pipeline isn't dreaming what it wants to see. The team runs them all. The spectrum holds. Impact today. Analog gravity crossed from cute demo to quantitative tool. Thermal spectra with tunable temperatures, superradiant amplification, partner correlations. These aren't posters, they're plots with error bars and systematics budgets. And they hand the liquid narrative a disciplined foothold. If horizon thermality is a fluid phenomenon in the lab, you can't dismiss gravity as emergent hydrodynamics as romantic. You must argue with numbers. But lab echoes are suggestive, not sovereign. The sky sets the law, so the next move was obvious. If the vacuum is a liquid and horizons radiate in fluids, then the vacuum's own optical properties should show fluid-like fingerprints when fields get intense. The hunt turned to a different kind of bench, lit not by cold atoms but by blinding magnets and lasers. The question waiting on the table, can empty space twist light like a medium? The anomaly stack, Flyby, Pioneer, and Frame dragging edges. Lab echoes are suggestive, but the sky answers with a puzzle we didn't order. Start with a maneuver every mission planner trusts, the gravity assist. You dive past a planet, trade momentum, and sling out faster. Energy bookkeeping should close to the last millimeter per second. For years, it mostly did, except when it didn't. A few Earth flybys returned tiny, stubborn residuals, millimeters per second that wouldn't die in the error bars. Software combed through atmospheric drag, Earth's oblateness, tracking geometry. The numbers twitched and then sat there, smirking. Stakes first. If space has a medium-like flow, a spacecraft slicing through a planet's rotating gravitational field might couple to something more than geometry, some subtle swirl or boundary effect. That's dangerous talk because general relativity already predicts a swirl, frame dragging. But if the liquid adds even a whisper of extra structure near massive bodies, navigation that bets on clean geometry could be missing a turn. Millimeters per second aren't sexy, but they decide whether a probe hits a corridor or kisses a planet. Action, a fresh hook arrived with a high-profile gravity assist. ESA's JUICE spacecraft skimmed Venus on its road to Jupiter. The community watched the Doppler like a heartbeat. After the correction arc settled, analysts whispered about S-level residuals, small but shaped in a way that revived the old flyby anomaly anxiety. Teams reached for the usual suspects: thermal recoil from warm panels, solar pressure model mismatches at phase angles, tracking biases during occultations. Each explanation shaved the residual, not erased it. Meanwhile, a handful of veterans pulled up a decade-old spreadsheet and added a new row. Another near miss. Parallel action across deep space, the Pioneer anomaly. In the 90s and early 200s, Pioneer 10 and 11 seemed to feel a tiny sunward acceleration, about 8 times 10m/s2. It smelled like drag. The medium camp perked up. Then the grind began. Thermal models got teeth. Radioisotope heaters warmed the bus unevenly. Photons carry momentum. Anisotropic heat becomes thrust. Years of archival work turned the mystery into math. The apparent acceleration matched what a warm radiator would push. The medium idea didn't die, it learned some humility. Heat, not hidden fluid, likely pushed the pioneers. But frame dragging never left the stage. Gravity Probe B spun ultra-precise gyroscopes around Earth and saw the geodetic effect and a tiny nod of orientation from Earth's rotation dragging spacetime. LAGEOS satellites, tracked by laser, felt the same precession. The metaphor writes itself. Geometry swirls like a very stiff fluid around rotating mass. The numbers hit general relativity's predictions within error bars. That success is a high bar for any liquid view. If a medium lurks, it must reproduce frame dragging exactly where we've measured it. Human moment. A navigation lead at a console in Darmstadt, eyes on a residual plot, mutters, "It's in the weeds," then refuses to go home. They rerun a light time correction with a different solar plasma model, reweight tracking passes that graze the ionosphere and watch the wiggle shrink. It doesn't vanish. They ping a colleague who worked the Rosetta flyby years ago. The reply is quick: "Check the station clock drift during handover." They do. The clock's clean. The plot doesn't blink. Someone jokes that the vacuum's taxing them a coffee. Impact so far. The flyby anomaly sits in a gray zone. Many cases folded under better systematics. Some residuals persist with shapes tied to geometry and approach angle. If a superfluid-like vacuum couples to motion near rotating, oblate bodies, the effect must be vanishingly small, at or below the clutter of thermal photons, plasma, antenna lobes, and clocks. That's a brutal design constraint for any liquid reality model. Hide within the weeds and still mean something. Meanwhile, the pioneer lesson stiffened the community's spine. Before blaming the medium, exhaust the mundane. Thermal recoil once masqueraded as new physics. Nobody wants a rerun. That caution bled into juice analysis. Blind pipelines, cross-agency ephemerides, independent orbit determination. Anything to keep wishful thinking out. The story's tension rose because the residuals lived in exactly the regime where a medium's drag, if it exists, should be indistinguishable from everything else. What nobody knew at the time early anomalies surfaced was how much frame dragging would anchor intuition. If geometry already flows the way a fluid analogy suggests, then the liquid story isn't asking to replace relativity. It's asking to underwrite it, to say, the swirl you measured is how a condensate with near-zero viscosity responds to rotation. In that light, flybys and Pioneer aren't proof, they're stress tests. Do boundary conditions, planetary spin, multipole moments, magnetospheres, create tiny interface effects of pure metric misses? If yes, they must scale with parameters we can predict and measure. Here's the pivot. If there's a medium, temperature matters. A real fluid has a spectrum. A warm bath leaves a taste. Accelerating observers might feel it as heat. That itch already has a name and a difficult reputation. If the vacuum is a liquid, its temperature should leave a taste. Drag, temperature, and the unruh itch. If a medium is real, it should have a temperature, or at least, acceleration through it should feel like one. That's the itch. The unruh effect says an accelerating observer doesn't see vacuum calm. They see a warm bath with a temperature proportional to their acceleration. Sit still and you see ground state. Fire your rocket and the same field looks thermal. If the vacuum is a liquid, this sounds like friction's cousin. But the promise cuts both ways. Warmth without drag in a perfect superfluid is a tightrope. Stakes first. If acceleration creates perceived heat, then detectors riding different motions disagree on what nothing feels like. That's not just philosophy. It ties into how we define inertial frames, how we design precise accelerometers, how we interpret radiation from fast electrons in storage rings, even how we think about rockets pushing against a medium. The danger is obvious. If there's real dissipation, actual energy lost to a background, then spacecraft should slow and clocks should bleed. They don't, beyond tiny explained terms. So the unruh itch has to be a kinematic effect, not a resistive one, if the liquid story is going to live. Action, what actually happens in the math. The unruh temperature is T equals Ha/2 pike B. You need wild accelerations to get anything human warm. At 1020 m/S2, you'd only reach a few thousand Kelvin. Lab gear can't push macroscopic detectors that hard cleanly, so experiments try clever routes. One path uses accelerated electrons in storage rings, looking for extra noise beyond standard synchrotron radiation. Another designs unruh wit, like detectors, two-level systems whose transition rates depend on acceleration. Others propose ultra-intense lasers to jolt electrons, so violently the unruh bath should imprint as stimulated emission. Each approach runs into a wall, backgrounds. What nobody knew at the time these proposals first circulated was how neatly some of the effects can hide inside known physics. Electrons in rings already radiate. Their quantum fluctuations look thermal in some frames. Sorting unrust-specific signatures from ordinary synchrotron light is like hearing a whisper under a jet engine. Laser ideas face Schwinger pair production and nonlinear QED clutter. The heat is real as a response function, but pinning it to a thermometer is brutal. Meanwhile, a parallel thread asks if the vacuum's medium nature should cause drag. A normal fluid resists motion. A superfluid doesn't below a threshold. If the vacuum's excitations have a gap or the spectrum forbids certain couplings at low energy, then uniform motion can be lossless. That maps well to relativity. Constant velocity observers don't see anything special, but accelerate and you can excite the medium. In a superfluid, that's when vortices shed and phonons fly. Translate back. Acceleration might couple to the vacuum's degrees of freedom and look like a thermal bath without creating a classical, frame-dependent wind. The line between perceived heat and real drag stays bright. The UNRA temperature is observer-dependent. Dissipation would be universal and is tightly bounded. Human moment. A small team in a basement lab stares at a cryogenic amplifier readout hooked to a superconducting qubit they're yanking with a precisely timed drive, an analog of an UNRA detector. They've injected fake signals blind, burned through weekends, and now the residual spectrum still shows a bump that shifts with drive amplitude the way the theory predicts. The pi rubs their eyes and says, "Swap the cables, again." They do. The bump moves. It wasn't the vacuum, it was the rack. Impact in the wider search. The UNRA itch keeps theoretical fire alive because it ties thermal behavior to horizons and acceleration, a theme that already showed teeth in analog gravity. It says you don't need a hot medium to feel heat. Motion writes temperature on your world line. For a liquid reality, that's both shield and target. Shield, because it explains why no ether wind shows up. Uniform motion is quiet. Target, because engineered accelerations or boundary conditions might coax measurable kinematic thermals that scale with parameters we control. Dissipation fear never fully leaves the room. If a medium exists, engineers worry about drag stealing delta V from rockets. The superfluid reply is crisp. Below critical velocities and in clean flows, there's no Stokesian drag. Inertia itself might be the vacuum's resistance to changes in motion, a coupling cost, without any steady bleed at constant speed. Some models try to go further, flirting with the idea that mass arises from interaction with the vacuum's modes, the way electrons get mass from fields in the standard model. If true, rockets would still push reaction mass. The medium isn't a propellant you can grab. It's the context that sets what push means. Now the T's. Strong fields can polarize the quantum vacuum. Nonlinear QED predicts vacuum birefringence. Light's polarization rotates in intense magnetic fields as if space were a weak crystal. That's not UNRA. That's the medium's optical fingerprint. Teams chase a sensitivity around Delton approximately 8 times 10^2. It's a brutally small index shift, but the hunt is systematic and rotation signals, if clean, would turn nothing into a steerable optic. Which brings the itch home. If acceleration paints heat on your frame and strong fields tint the vacuum's refractive index, then careful setup should let us translate motion and field into tiny, measurable currents of information through empty space. One proposal turns light into a current through the vacuum. No plates, just intense fields and polarization control to pull a whisper of conduction from nothing.